For as long as humanity has gazed up at the night sky, we've asked the most profound question of all: are we alone? We've sent probes to distant planets, listened for signals from the stars, and peered through powerful telescopes, all in the hope of finding an answer. But what exactly are we looking for? When we talk about finding alien life, we're not just looking for little green men. We're looking for the very foundation of life itself. And on Earth, that foundation is built on a single, unassuming element. This is a story about chemistry. It's a journey to the atomic level to understand why all known life, every plant, every animal, every microbe, is inextricably linked to the element carbon. But is this a cosmic rule, or simply a lucky coincidence for our planet? Is it possible that life could exist without carbon? And if so, what might it look like? This is a fundamental question in astrobiology, and the answer might be stranger than you can possibly imagine. The first and most crucial reason is carbon's unparalleled versatility in bonding. A carbon atom possesses 4 valence electrons, which means it can form 4 incredibly strong, stable covalent bonds. This might sound like a simple detail, but it's the key to everything. Think of it as having 4 hands, ready to link up with a wide variety of other atoms, including other carbon atoms. This versatility allows it to form not just single bonds, but also double and even triple bonds. This ability to form different types of connections is what allows carbon to act as the central scaffold for an immense and diverse array of molecules. Unlike other elements that are limited in their bonding options, carbon is the ultimate connector, capable of building intricate and complex structures with almost limitless possibilities. Building on its versatility, carbon's second major advantage is its ability to form incredibly complex and intricate molecules. By linking with itself and other atoms, carbon can create long, stable chains and complex rings that serve as the backbone for the most important molecules in biology. This is the foundation of the 4 major macromolecules of life. Carbohydrates are long chains of carbon that store energy, while lipids, with their complex carbon structures, form cell membranes and serve as another form of energy storage. Proteins, the cell's workhorses, are long chains of amino acids, each built on a central carbon backbone. Finally, nucleic acids like DNA and RNA, which hold the genetic code for all life, are complex polymers with a central carbon framework. In essence, carbon is the scaffold upon which all life is built. The complexity required for a living system, to store information, catalyze reactions, and maintain a physical structure, simply isn't possible without an element capable of forming these vast, 3-dimensional molecular architectures. The third reason is a perfect balance of stability and flexibility. The bonds that carbon forms are often described as being in the Goldilocks zone. They are strong enough to hold complex molecules together in the dynamic, watery environment of a cell, so they don't just fall apart. But they are not so strong that they can't be broken and reformed. This balance is crucial for metabolism. The very process of life, taking in energy, building new molecules, and breaking down old ones, requires bonds that can be manipulated. If the bonds were too weak, all our molecules would dissolve. If they were too strong, all our biological reactions would be impossible. Carbon's bonds are just right, allowing for a chemistry that is both durable and dynamic. The final key factor is abundance. While carbon's unique properties are its primary advantage, it also happens to be one of the most common and readily available elements in the known universe. Carbon is created in the hearts of stars and is a key component of planets and cosmic dust. It's everywhere. The fact that carbon is both chemically perfect and cosmically abundant means that it was readily available for life to evolve from the earliest moments of our planet's formation. Why silicon isn't a good stand-in for carbon? Before we get to that, if you're enjoying this deep dive into the chemistry of life, do me a favor and hit the like button. It really helps us out. And if you're as curious as we are about the universe and all its mysteries, be sure to subscribe so you don't miss our next video. The element silicon has a similar electron configuration to carbon, which is why it's often considered a potential alternative. However, a closer look at its chemical properties reveals why it's highly unlikely to support life as we know it. Silicon atoms are larger than carbon atoms, and this size difference has significant consequences for chemical bonding. The bonds that silicon forms with other silicon atoms are much weaker and less stable than carbon's bonds. This weakness makes it difficult for silicon to form the long, complex chains and intricate ring structures that are essential for building biological molecules like proteins and DNA. In a water-based environment, these silicon-based chains would simply break down. A key difference between carbon and silicon-based chemistry is what happens when they oxidize. When living organisms on Earth metabolize carbon, the primary waste product is carbon dioxide, a gas that is easily expelled. In contrast, when silicon oxidizes, it forms silicon dioxide, which is a solid, also known as sand. For a theoretical life form, trying to excrete a solid like sand would be incredibly inefficient and potentially impossible, leading to a constant buildup of waste that would halt metabolism. Carbon's ability to form single, double, and even triple bonds gives it the versatility to create a vast array of molecules with different shapes and functions. Silicon, on the other hand, is far less likely to form double or triple bonds. This limited bonding ability would severely restrict the number and complexity of molecules that could be created, making it difficult to achieve the diversity needed for life. Silicon compounds are also highly reactive with water. In a process called hydrolysis, the long chains of silicon atoms would break apart when exposed to water. Since liquid water is considered the most probable solvent for life in the universe, this property is a major obstacle for silicon-based life. While the universe may hold countless possibilities for life, the fundamental chemical properties of silicon make it a flawed candidate for creating the complex, dynamic, and stable structures necessary to support life. So while carbon may reign supreme in our corner of the cosmos, a true testament to its unique and perfect chemistry, the universe is a very big place. Our search for life has only just begun. And while we continue to look for liquid water and the signature of carbon, a small piece of us hopes to find something so wildly different that it challenges our every notion of what it means to be alive. So what do you think? Could silicon-based life exist on a world with a very different chemistry? Or is carbon truly the only element with the perfect set of skills to create life? If this video sparked your curiosity, please consider hitting the subscribe button and giving it a like. Your support helps us create more content just like this.